Hi, so welcome everyone. So I'm Jeffrey Everts, and I think I hope today to give you a different perspective on how electrical charges can emerge in soft matter systems. Before I start, I would like to thank some of my collaborators who contributed to this work. So for example, Bogdan, Haridas, and Ivan were involved in an experimental part of this work. Micha was my theoretical supervisor when I did a postdoc in Ljubljana. Chao and Jaroslav worked on some theory, and I would also like to acknowledge Anja and Rudolf Gornik, who unfortunately passed away, as we have know, in the last part of this talk. So it's some ongoing work. So I don't think that this needs a lot of introduction because most people here work on charge systems. So we all know the concept of a so-called electric double layer. So if you think about a charged surface that you, with surface charge sigma, you immerse it into water, for example. Due to the Coulomb interactions, the ions want to be as close as possible to the charged plane, but due to entropy, they want to also be as homogeneous as possible in the solution. So these two competing effects lead to the formation of a so-called electric double layer. So there's two layers of charge, a surface charge density at the surface and a diffuse ion cloud that screens the surface charge. So typically, what you can do is you can describe, for example, in the most simplest case, mean field point like ions. You can use the Poisson-Boltzmann equation. You can solve for the electrostatic potential, here may dimension this, and the ion density profiles. And we all know that there's a characteristic length scale called the Debye screening length, which shows the far field decay of the ionic profiles and the electrostatic potential. And these electric double layers have a myriad of applications. So think about energy storage, but also in plasma physics, electric double layers occur, in DNA, as we have seen, and also colloidal suspensions. So in this talk, however, I want to, so what we do mostly up until now in this workshop is that we assume that the medium is, for example, water or some other solvent. So it's typically an isotropic medium. In this talk, I would like to change gears and ask the question, what happens if this medium has some, it's not isotropic, but it has some anisotropy associated with it. So for example, what you see on this slide is a cross-polarizer's picture of a nematic liquid crystal. So you see here, so a nematic liquid crystal, I will explain it for the people, probably you know, but I will explain later what it is. So you see a very rich structure under the microscope, which denotes regions of local orientational order. And you have also these very interesting type of structures, which we call topological defects. And basically, the whole talk is about what happens if you add salt to such a system. So what are liquid crystals? So as the name suggests, so they are both liquid and crystal at the same time. So I think the easiest way to understand it is that when you think about a simple model system, for example, hot-like particles, then if there's no ordering in center of masses of these rods and no ordering in terms of orientation, then we call this an isotropic phase. So these are like typical liquids that we all know. On the other side of the spectrum, when we have complete translational order, but also orientational order, it's called a crystal. So everything in between is a liquid crystal. So you have, you break, for example, part of the orientational, part of the rotational symmetry. So you get, for example, a net alignment of these rods. Then you get a nematic phase. Do you also break translational symmetry in one dimension, you get the so-called smectic phase, but you can also do it in reverse. You can first break translational symmetry of the isotropic phase, but leave the rotational symmetry intact, then you have a plastic crystal. The liquid crystals can occur in molecular form. So one popular molecule is 5Cb. which we also call thermotropic liquid crystals, because they become liquid crystalline as function of temperature. But they're also like colloidal systems that become liquid crystalline, such as the tobacco mosaic virus, which is a colloidal liquid crystal. So it has vastly different dimensions from molecular systems, which also can be taken into consideration. So why liquid crystals? So if you have this, for example, in the nematic phase, a net alignment of these rods, so depending on how you deform it, you get, for example, an elastic response. So that's why there's the crystal part of liquid crystal. Sometimes it behaves like a solid. So there's an elastic energy cost associated with certain deformations of a liquid crystal. But sometimes it can also flow like a liquid. So for example, these are like experiments, quite recent, about what happens if a flow is induced in, for example, a liquid crystal where the liquid crystal is aligned in the z direction. And you can get all kinds of interesting orientational and topological structures. So as I said, I want to combine the two, so liquid crystals with ions. And this is kind of a challenging thing to do, because you have to combine statistical mechanics with electrostatics, topology, and in this talk, I would like to discuss some of the salient equilibrium and non-equilibrium effects associated when you combine these two systems. So how are liquid crystalline systems different than, for example, isotropic liquids like water? So I will go through the main type of couplings you can expect between the orientational order and the electrostatic effects. So one of them is the dielectric coupling. So the dielectric coupling is basically emerges because in a liquid crystal you don't have just a dielectric constant, but you have a dielectric tensor, because there's a net alignment of the medium. So you get an anisotropy also in the dielectric properties. So when you plug it into the free energy, it will lead something like delta epsilon, which is basically for example, in the nematic phase, you have two independent components of the dielectric tensor, and this delta epsilon quantifies the difference between the two. And you get a term N, which is the average alignment of the molecular building blocks of the liquid crystal, dot E. So what this dielectric coupling does actually is that depending on the sign of this delta epsilon, the liquid crystal either aligns with the electric field or doesn't want to align. This kind of couplings is, for example, used in LCD screens. Yeah? So if you have an LCD screen, it's basically a Frederick's effect, it's called. It stems from the fact that you have dielectric anisotropy. Different effect that emerges in liquid crystals is the so-called flexoelectric effect. So if you think about these, for example, molecules that have an anisotropic shape, that they are dressed with an electrical dipole, and you deform such a material, then if you deform it in the correct way, you can induce a macroscopic polarization. So liquid crystals are also interesting because of this, because deformations can lead to polarization. This is called the flexoelectric effect. And furthermore, there's also what we introduced later in the theory is also so-called ion partitioning effect. So this means basically that suppose you have an isotropic liquid phase and a nematic phase adjacent to it, then depending on the Gibbs transfer energy, which is the free energy that you need to transfer an ion from the isotropic phase to the nematic phase, the ions prefer to be in the isotropic phase or in the nematic phase. So now I would like to guide you through a few of these effects where all of the previous couplings kind of emerge in increasing complexity. One of the first things that we did with liquid crystals and ions is the concept of anisotropic screening. So we all know there's a lot of word around in this conference already about the electrostatics around the charged particles. And we asked the question, okay, what if you have a particle immersed in liquid crystal that is charged? How does, for example, the electrostatic profile look like, and how do the particles interact? So first of all, as I mentioned before, the liquid crystals, they can behave elastically depending on the deformation modes. So what you see here is a type of particle that is emerged in a liquid crystal. So you have, so these green lines denote the average orientation of the liquid crystal, and the particle is treated in such a way that the average alignment of the liquid crystal molecules are perpendicular to the surface. Since the far field is homogeneous, and it has to be perpendicular to the spherical surface to match the two let's say, alignments, you cannot get away with it without creating a defect around the particle. So this is an example of such a defect. It's called a Saturn ring defect. So these are like the collection of points for which the orientation of a nematic molecule is ill-defined. So if you bring together two of such particles, and so we take them for now uncharged, you can imagine that if you close the distance between these two particles, you will also change the local orientation of the molecules. And depending on how you change it, you can get basically, you either increase the elastic free energy or you decrease it. So what you see for uncharged particles with a Saturn ring defect, so two particles with a Saturn ring defect, is that the elastic interaction in a multiple picture looks like this. So there are directions in which the elastic interaction is attractive, but there are directions also where it can be repulsive. So this is like a slide where you can see it. So for some directions, it's basically they are separated, and for other directions, they come together and form a dimer. So for example, this is one direction. This is an experiment where you release a pair of particles, and they can perform Brownian motion, and there are certain angles for which they can come into contact. So this is kind of well known in the liquid crystal community. So we thought about, okay, what about charged particles? So we added the effects of electrostatics, van der Waals interaction, and nematic elasticity. So as I said before, what happens is that what changes with the classical picture on isotropic liquid is that instead of a dielectric constant, you have a dielectric tensor. So what one has to do basically is to solve the Poisson-Boltzmann equation with an anisotropic dielectric tensor. So this is an example of such a solution. So you have a spherical particle. Here we assumed that the director field is homogeneous in the z direction. And so depending on the tensorial components of this dielectric constant, you can get either, in this case, you get a prolate spheroidal shape. So you get basically, instead of a spherical double layer that you would get in an isotropic medium, you get an extended double layer. And actually, if you assume, for example, small electrostatic potentials, you can even find an analytical formula for the decay, for the Debye screening length in a sense. And you find that depending on how you transverse radially from the particle with respect to the z-axis, so this is this theta, the Debye screening length is different. And you can find an analytical formula for which, so these are the tensorial components of this dielectric tensor on a certain basis, and you can see there's a clear angle dependence in this work. So indeed, so you find, so the full lines are the numerical computations, and the dashed lines are the analytical formula. So now we have solved the single particle picture. So we went on to look at interactions, because this is something they can measure in experiments. So this is a pair of particles that they released with optical tweezers, and then they looked at which angles they kind of stay together or are repelled or not. So we were able to compute the effective interaction within the Debye-Huckel-like theory, in a certain sense also analytically. And we saw that so the black dots are like kind of the equilibrium separations of a pair of particles, and the color map is the theory. So the blue means attraction, and the red means repulsion. So there is a small region where there is, let's say, where there is a metastable state where the particles prefer to be, and the theory matches the experiments quite well, I would say. So these are like a list of points for which they like to be around this angle. So this is vastly different than, for example, the RVO type interactions, where you have a screen Coulomb that's compensated with an energy barrier, where you have the van der Waals interaction, van der Waals interaction with screen Coulomb, so you have an energy barrier. But you have here also this small metastable minimum due to the effects that you have competition also between electrostatic and elastic interactions. And it must be noted that if you would have neglected this dielectric tensor, so if we would have assumed an isotropic dielectric constant, then this minimum would have shifted by around 10 degrees. So this anisotropic effect of the dielectric constant does show up in the effective interaction between a pair of charged particles in a liquid crystal. Another effect that we looked at, so now we will increase the complexity, is that in liquid crystals there's the possibility to form so-called topological defects. So this is like a collection of points for which the orientation of the liquid crystal is ill-defined. So what happens then is when you have such a defect, the core of the defect is always associated with a very high elastic energy cost. So what happens is that the core of the defect is always molten. So what you see inside this green tube is basically an ordinary / isotropic liquid. So outside of this green defect, you have a nematic ordering, with a complicated nematic texture. So this is one cross section. You see this is an example of a topological defect, because in the center the orientation is ill-defined. So there's a region where it's molten and outside it's nematic. So the question that Mia at the time asked was, okay, how would ions redistribute around such a topological defect? So I don't want to, in the light of time, I don't want to go too deeply to the theory, but what we did is we actually solved the Landau theory for the liquid crystal coupled to the Poisson-Boltzmann theory. And then if you do this numerically, you can get the ion profiles out of it. So as I said in the beginning from the talk, there are like various effects of the liquid crystals. So we turned them off by hand to see what each term on the free energy did. So first we looked at the effects of ion partitioning. So this is basically an effect that says whether the ions prefer to be in a liquid phase or in a nematic phase. And indeed what we found is that using this effect, the ions can, depending of course on system parameters, there is a possibility that ions can preferably reside in the center of a defect core. So we looked at two types of defects. I never remember which one. One is -1/2 defect, the other one is +1/2 defect. Because of this ion partitioning effect, the ions prefer to be in the core of the defect. Why? Because in the defect core is molten, so there is a preferential solvability for ions within the core. Then we looked at the effect of flexoelectricity. So flexoelectricity is basically, I repeat again, so that deformation leads to macroscopic polarization. So there you can see actually that the flexoelectricity basically gives rise to a charge distribution around a defect that looks kind of interesting to me. It's actually very easy to understand why these profiles occur. Namely, so with this, so each nematic texture generates some polarization texture, which follows from the constitutive relation which gives you between the nematic order parameter and the polarization. From it, you can deduce a bound charge density, and the ions typically redistribute to minimize they reside in regions where the bound charge density is high due to polarization. That's why you get these kind of patterns of charge distributions around some nematic textures. And if you combine the two, you get a superposition of the two effects. So you get preferably ions that reside in the core of the defect, and then with some interesting effects due to the flexoelectric effect. And here I would like to emphasize that these charging effects of defects are actually, you do not need to have external charge surfaces for it, because typically we have in mind that, okay, an electric double layer forms next to a charged surface, but here okay, you need a surface to stabilize a defect, that's true, but the charging happens mostly in the bulk of the liquid crystal, and that's why I think it's kind of an interesting effect. How much time do I have? 4 minutes, okay. So I have, you can also ask the question, how do ions redistribute around a colloidal sphere, for example? So you have, you can play with two types of things. So as I said, like in the previous example, you can have a sphere where the liquid crystal building blocks want to be perpendicular to the surface and the far field is in the z direction. So you can glue these two director fields in two ways. You can either generate a point defect below the particle or Saturn ring defect around the particle. And if you then look at this electric double layer structure around such a type of defect and a spherical charged particle, no, this is an uncharged particle, by the way, you get electric double layers that kind of look fancy because you have regions where you have negative charge alternating with positive charge. And this is, by the way, an electric double layer when the particle itself doesn't carry an extra surface charge. This is only for the flexoelectric effect. And of course, for the point defect, you have a similar effect. Here, I plot the isosurfaces of the plus and minus ions. I think the final, what you can also do is you can ask the effect of topological defects close to charged surfaces. So we also looked at that. So now, until now, it's only into the bulk of the liquid crystal. And what we actually found is that when you have a topological defect around the particle, so the surface charge is actually influenced by the local nematic texture close by. So actually what can happen is when you, for example, if you would shrink a Saturn ring to a point defect, then the charge distribution on the particle can change. So you can actually, hopefully, I don't know how practical it is, but topological defects can give a means to control, for example, surface charges. Awesome. So actually, I have also something on the non-equilibrium effects, but maybe on the view of time, it's best to maybe leave it out. Okay, so maybe I can go quite quickly through it. So up until now, we have only looked at equilibrium. So at a certain point, we thought also about non-equilibrium effects. So here we have we had an inspiration from spintronics. So spintronics is basically the field where you manipulate the quantum mechanical spin for electronic applications. So there are two main driving forces behind this field, namely the concept of a spin torque and for spin pumping. So what does spin torque mean? It means that if you drive an electric current through a magnetic texture, it will lead to movement of texture. And the spin pumping basically is if you move magnetic texture, you can drive electrons. So you pump electrons by spin. So in spintronics, you have a magnetic order parameter, but we ask the question, what happens if you change the magnetic order parameter to the nematic order parameter? So can we replace spins by nematic director and electrons by the ions? And the answer is yes. So using methods of non-equilibrium thermodynamics, you can derive constitutive relations for the director. So the director is the average alignment of liquid crystal molecules and of the charge. So this, of course, is in certain approximation. These two are related by Onsager reciprocal relations because you have microscopic time reversibility. And what it basically does is like, okay, so if you have a nematic texture and you drive an ionic current through this texture, you can basically move this texture due to ionic current, but if you have a means to change the texture, you can generate actually an ionic current. So these two are two reciprocal effects, very similar to the Lehmann effect in liquid crystals. You notice that it is very similar to that of how an Archimedes screw works, because an Archimedes screw is this ancient machine where you can pump water to higher altitudes, or you can generate electricity by letting water go from high to low. We kind of imagine the charge dynamics in liquid crystals. And one interesting effect is that it will generate an extra electromotive force if you introduce this coupling, which has an impedance that is of an inductive form. So if you would like to make equivalent circuit models for electrokinetic cells, you can model them also by inductive elements, which is not so common, for example, when you look at isotropic systems. And so there's also a means to move defects with an ionic current. So this is also one of the resulting things that came out of the theory. And to conclude, I would also like to give a small tribute to Rudolf Podgornik, because actually I was working with him on some project on viruses. So we had, as we all heard before, is the virus is a carrier of the genetic material, and really once contacted me to ask the question, not what if the DNA inside the virus is nematically ordered? What kind of electrostatic effects can you see there? And together with Anje, who is in the public, we are trying to finish this project now. Really is not here anymore. So what we found is that we made this kind of a teaser slide, so I will not explain too much, but we were interested in what happens if you have a virus particle inside the DNA is nematically ordered, and can you then see the anisotropy of the system inside the particle? Will it also propagate outside the capsid? The answer is yes, with remarks, I think. So, so this is so. I would like to conclude with some take-home messages. So I hope to introduce you to the fascinating world of liquid crystals and how charge effects also can play an important role here, and especially since many people here are working on biomolecular systems, I think maybe at some day it will be very relevant, but maybe also not. Thank you for your attention.